Hello everyone, I welcome you back for another tutorial of artificial intelligence. I'm Lubinga Hudson from Uganda. Today we are going to look at the problem solving, and this is gonna take us two parts. So this is the first part, part one of problem solving. Please don't forget to subscribe to my channel and invite other people, your friends, to also watch and learn more about artificial intelligence. This lesson is going to take us through the introduction to problem solving, the problem solving agents, and then we shall look at problem solving by searching. So let's first have an introduction to problem solving. What's problem solving? Now, this word problem solving may have different meanings according to the context. So, in the context of psychology, a problem solving refers to that state where we wish to reach a definite goal from a present state or condition. So, you are in one state, there is another state that's a definite goal where you want to reach. You move from one state to that state, which is the goal. So from a present state or a condition to a preferred condition. So according to psychology, that is problem solving. But now according to computer science, a problem solving is part of artificial intelligence, and this kind of artificial intelligence encompasses or it includes a number of techniques, and these techniques include algorithms, heuristics, and so on that are used to solve a problem. This word heuristic in this sense of computer science is it means a mental shortcut that allows people to solve problems and make judgments quickly and efficiently. Let's talk about the problem solving agents. Remember, we have already looked at the types of agents. Now, a problem solving agent is first of all a goal driven agent, meaning it's driven, it's an agent aimed at fulfilling a certain goal. So this agent focuses on satisfying the goal. Now, these are the steps that are performed by a problem-solving agent. There are basically two steps. The first step is goal formulation, and the second step is the problem formulation. So for a goal-solving agent to solve or to reach a particular goal, one, it has to there must be goal formulation. What goal is it aimed at achieving? And after knowing that goal, then it will have what we call the problem solving. What steps is it gonna take in solving the problem so that it reaches that particular goal? So goal formulation is the very first step and the simplest step in problem solving. Under goal formulation, we have steps or a sequence of steps that this goal-driven agent is required to formulate. At least there must be one goal out of multiple goals, and then there are certain actions that it will undergo to achieve that goal. So this goal formulation is based on the current situation and the agent's performance measure. Now, the other step of problem formulation is the most important step of the problem solving, and this is the step that decides what actions should be taken. What should the goal-driven agent do in order to achieve the goal that has been put in place, the goal that has been formulated? These are the components involved in this second step. The second step of problem solving, the second step performed by the problem solving agent. So these are the components involved in the problem formulation step. So there are basically 5 steps. We have the initial state, actions, transition model, goal test, and the path cost. The initial state, as you may think, is the starting state or the initial step of the agent that it undergoes to achieve a certain goal. Then the actions, these are the possible actions. It's the description of all the possible actions that are available for the goal-driven agent. Then the transition model describes what each action does. So the actions are all the possible actions available, but now the transitional model tries to describe, to explain what happens in each action. And the goal test is what determines if the given state is a goal test. So the goal test is put forward to show, to ensure, or to test whether the agent has reached a particular goal. Then the path cost is measured using what we call a numeric cost. So this cost is assigned to each path that the goal-driven agent will follow in order to achieve the goal. Now the problem-solving agent selects a cost function which reflects its performance measure. So the problem-solving agent doesn't just solves a particular problem, but it follows a certain cost function, and the way the goal-driven agent performs these actions, there is a performance measure that is put forward. Now remember, its aim is not just any solution, but the goal-driven agent will always need to find an optimal solution. This is the solution that has the lowest path cost among all the solutions. So it always looks for the best solution, the solution that has the lowest path cost. How is this path cost measured? Remember, we said that it uses a cost function, and the path cost, each path is assigned a numeric cost, and it's this numeric cost that is used to determine if the path is the one that has the lowest cost, and therefore it's that path that gives the optimal solution. Now these first 3 steps, the initial state, actions, and transition model, they together define what we call the state space of the problem, indirectly or implicitly. This state space, remember we said it includes the initial state, actions, and the transition model. So that state space of a problem is a set of all the states which can be reached from the initial state, followed by a sequence of actions. So the state space forms a directed map, or at times we use graphs, and in that map or the graph we have what we call the nodes are the states. Then we have links between the nodes, those are the actions, and then the path is the sequence of the states connected by the sequence of actions. So we shall be using trees as our examples. We shall get to know more about the nodes and the path and the links. Now, as this goal-driven agent is searching, we are here. It identifies all the best possible sequence of actions to reach the goal state. So it begins from the initial state, going to the goal state, but it goes through all the possible sequence of actions, not just any path, but the best. It takes a problem as an input and then returns the solution as its output. Now this solution that the goal-based agent finds is found using the best algorithm out of the various algorithms, which may be proven as the best optimal solution. What about execution? The goal-driven agent will execute the best optimal solution from the searching algorithms to reach the goal state from the current state. So it uses, after finding the optimal solution, now it will execute that solution from the searching algorithms. Okay. Let's see examples of problems that we are talking about. The examples of problems that are solved by this goal-driven agent. Now, basically, there are two problem approaches. One is the toy problem, and two is the real-world problem. What's the toy problem? It's a concise, that means brief or simple, but detailed and clear. So it's a concise and exact description of the problem, which is used by the researchers to compare the performance of algorithms. So you have some problems that we can use to compare how our algorithms do perform. So we formulate a simple problem, and now we subject several algorithms to it, and we use it to find to find the optimal solution or to solve a problem. And now we compare the performance of those algorithms. So these are what we call the toy problems. Then we have the real world problems. So in the real world problems, we require real world solutions that are applicable in our day-to-day lives. So unlike a toy problem, the real world problem doesn't depend on descriptions, but we can have a general formulation of the problem. So these are some of, we are going to look at two examples of toy problems. Let's talk about the 8 puzzle problem. Now, here in the 8 puzzle problem, we have a 3x3 matrix. So this is what we mean. We have 1, 2, 3. Those are rows by 1, 2, 3 columns. So we have a 3x3 matrix, and this matrix it has movable tiles. These are the tiles. They are 8, 1 to 8, and these movable tiles have in between, or there is a space that is left that is blank. Now the tile that is adjacent to the blank space can slide into that space. So you're seeing 2 is adjacent to this space. You can slide 2 and put it in this position. 6 can slide also and go to this position. The same applies to 5 and 3. So those are the tiles in this case that are adjacent to this blank space. In this second diagram, we have 1 and 3 are the 2 tiles that are adjacent to this space, so they can slide into that space. Now the objective of this puzzle is to reach a specified goal, which goal is the one that is similar to the goal state shown in this figure. So this is the start state, the initial state, when everything is disorganized. These tiles are not arranged in any order. So your goal is to ensure that you arrange these tiles so that they are arranged in ascending order from 1 up to 8. And you do that by moving or by sliding these tiles using the blank space, so that in the end your goal is to have this arrangement. So your task is to convert the current state, this state or the start state, into the goal state, this one, by sliding the digits into the blank space. So this is a simple toy problem, the 8 puzzle problem. Let's further analyze the puzzle problem by going deep into the problem formulation steps, as we've already looked at them before. And now let's be specific using this. They are the 8 puzzle problem. We have the states. So for this problem, it describes the location of each numbered tiles and the blank tile. That is those are the states. All the numbered tiles plus the blank space, a combination of all those are the states. Then the initial state can be any state. Like in this diagram, this is our initial state. That's the arrangement that we have, and the blank space is in the middle. Then we have actions. Here, now the actions of the blank space are identified. You either slide from the position of the tile to the left, to the right, up or down. So that's those are the actions that you do. So you can slide 2 down, 3 up, 5 to the right, and 6 to the left. So those are the actions that are if it's a problem solving agent, it will make those actions. Then we have the transition model. Remember, we said that the transition model describe what each action does. So here, the transitional model, we are saying it returns the resulting state as per the given state and actions. So when you move from 5, to the right and it goes in this blank space, what it returns after moving that 5, now the nature of the state of the puzzle is the transition model. After making an action, what is returned. Then the goal test, it identifies whether we have reached the correct goal state. So our goal state is this one, to have our tiles arranged in ascending order from 1 to 8. Then we have the path cost. The path cost is the number of steps in the path where the cost of each step is 1. So our path cost, it depends on how many steps you make to reach this goal state. Someone may use, for example, I'm just giving an example, 20 steps. Another person may use 50, and so on. But whichever step you make, whenever you slide a tile and it goes to the blank space, then that step, for this kind of problem, each state, the cost is 1. Note that the 8 puzzle problem is a type of sliding block problem which is used for testing new search algorithms in artificial intelligence. Now let's have another example of a toy problem. We have what we call the 8 queens problem. Now the aim of this problem is to place 8 queens on a chessboard in an order where no queen may attack another. So this is our start state and the goal state. Our aim is to have these queens arranged in an order in which they do not attack each other. What do we mean by attacking? A queen can attack other queens either diagonally or in the same row and column. For example, here, this is queen 1. When I move this queen in this diagonally, this is what we mean diagonally, in that angle. When I move queen 1, it will reach a time and it will attack queen 5. So that is diagonally. When I go this diagonal, there is nothing. This is now the row. When I move it in a row or in a column, for queen 1, its column, there isn't any other queen and in its row, but diagonally it will attack another one. So that means this start state, for example, here has some issues. So our aim is to ensure that we have something like this, whereby when you look at, for example, this queen, this is its column, there is no any other queen, and in its row there is no other queen. Then diagonally there is no other queen, and in this diagonal still no other queen. So whichever direction, diagonally, up, down, it doesn't attack any queen. The same applies to all these other queens. So there can be several arrangements. There is not only one definite solution. So that's the 8 queen problem. So from this figure, we can see that this is a correct solution. Okay, so that's the 8 queens problem, and that's an example of the toy problem. Now, in this kind of problem, that's the 8 queens problem, there are 2 main kinds of formulation. We have incremental formulation, which starts from an empty state. That is, you may have your chessboard without any queen when it's empty, and now you keep on adding queens at each step until you make moves, and you have the arrangement as required by the goal state. So the following steps are involved in this kind of formulation, the incremental formulation. We have states. Here you arrange the queens from 0, from empty to 8, because there are 8 queens on the chessboard. So those are the states. And then the initial state is an empty chessboard. Then the actions are what you do when you are adding the queens to an empty box. You are making an action, and the transition model returns the chessboard with a queen added. So whenever you do an action and you add a queen, what is returned is the transitional model. Then the goal test, you're checking whether the 8 queens are placed on the chessboard without attacking each other. So that's your goal test. And the path cost, we are saying there is no need for path cost because only final states are counted. In this formulation, there is approximately 1.8 times 10 power 14 possible sequence to investigate. So if you multiply this, you get possible sequences that you can investigate in order to reach a particular solution. Okay. Another kind of formulation is the complete state formulation. So this one starts, unlike the incremental formulation, the complete state formulation starts with all the 8 queens on the chessboard and moves them around, saving from the attacks. So here you start by placing randomly the 8 queens in any position on the chessboard. Then you start making the moves until there's no attack. So this state of formulation, the complete state formulation, involves 2 steps. We have the states and the actions. The states, we are talking about the arrangement of the 8 queens, 1 per column, with no queen attacking the other queen. And the actions, you move the queen at the location where it is safe from the attacks. So this formulation is better than the incremental formulation because for it reduces the state space from 1.8 times 10 power 14 to something, to a lesser figure, 2057, and it's easy to find the solutions. Okay. Now let's also talk about some examples of real-world problems. We have this common problem called the traveling salesperson problem, the TSP, traveling salesperson problem, TSP. Now, in this problem, we have what we call a touring problem, whereby we have a salesman who visits each city only once. So this is a person who is selling some stuff and visits each city only once. So the objective in this problem is to find the shortest tour and sell out the stuff in each city. For example, consider this graph shown in this figure. This is a graph, and these are what we call the nodes. 1, 2, 3, and 4 are what we call the nodes. Now, this movement from 1 to 3 is what we call a path. A link. And when you have more than 2 links, or even if it's 1, if you move from a starting point to the end point, that is what we call the path. Now, this traveling salesperson problem tour graph that we are seeing we have 1 to 2, then 2 to 4, and then 4 to 3, and 3 to 1. So the cost tour is 1 to 2. This the path here has 10, then 2 to 4 we have 25, and then 4 to 3 we have 30, and then 3 to 15 we have 3 to 1 we have 15. So when we get the sum of this, when we add, the answer is 30. So this is the cost of our tour, the cost of the path, and this is the shortest path. So if you wanted to move from 1, that's the start node, and then you travel, you go through, you reach each city, and then you come back to the starting node, you will find out that this is the shortest path. 1, 2, 4, 3, and then 1. Okay, because if you move from, for example, 1, 4, 2, 3, 1, let's try to see the path. This is 1 to 4, that is 20. 20 plus 25, that is 45, plus 35, that is 75, and now 75 plus 15, that is 95. Okay, so you see that that cost is not the best one. It is not the lowest. So this is the lowest cost, and that's the traveling salesperson problem. Okay. Now we have the VLCI layout problem. VLCI is short for very large scale integration, and here we are talking about the computer circuits, whereby you have millions of components and connections that are positioned on a single chip. So in order to maximize the area, the circuit delays, and the stray capacitances, and maximizing the manufacturing yield, you have to use a particular arrangement. So to solve this problem, still you need artificial intelligence. You can go and make more research about it, but this is another example of a real-world problem. Okay, now let's talk about problem solving. Having seen what a problem is, the types of problems, and some examples, we are going to see now problem solving by searching. So we're gonna look at some searching solutions that are available for goal-based agents, goal-driven agents, to solve particular problems. So we have seen many problems now there's a need to search for solutions to solve them. So in this section, we are going to understand how searching can be used by the agent to solve a problem. For solving different kinds of a problem, an agent will make use of different strategies to reach the goal by searching the best possible algorithms. So here we use certain algorithms, such algorithms, to solve these problems. So the process of searching is also known as the search strategy. Now, whenever we use a certain search strategy or an algorithm to solve a problem, that algorithm has what we call the performance measure. We shall not be going into details of the performance measure of each algorithm, but we assess and compare each algorithm depending on the performance of the algorithm. And the algorithm is measured based on these four aspects. We have completeness, optimality, time complexity, and space complexity. Completeness means, this is the measure to check if the algorithm guarantees to find a solution. That is, if the solution exists. So completeness, we have to ensure that our algorithm is capable of finding a solution. Then optimality. This one measures if the strategy searches for an optimal solution. So optimality, we are checking whether our algorithm can get the optimal solution, can find the best solution. Then time complexity. This is the time taken. How long does our algorithm take to find a solution? And space, we are looking at the amount of memory that the algorithm will require. Memory, we are talking about the space on the computer memory. How much memory is required by our algorithm to perform a search? So the complexity of an algorithm depends on branching factor or the maximum number of successors, the depth of the shortest goal node, i.e. the number of steps from the root to the path, and the maximum length of any path in a state. So time complexity or complexity is general, but in complexity of an algorithm, we have the time complexity and the space complexity. So how long that's time complexity and how much memory required, that space complexity. So to determine the complexity of an algorithm, it depends on a number of factors. How many nodes, how deep or how shallow does the algorithm go? How many nodes does it visit to arrive to the goal? To the goal. Okay, and what is the path? What is the cost of the path that the algorithm must take to find the optimal solution? So by doing that, we can determine the time complexity and the space complexity of an algorithm. Now let's talk about the search strategies or the search algorithms that exist. These are basically divided into two parts. So there are two types of strategies that describe a solution for a given problem. We have what we call the uninformed search or the blind search. This is the type of search strategy that doesn't have any additional information about the states except the information provided in the problem definition. So it doesn't have any additional information, and therefore that's why it's also known as the blind search. Then these are the examples or the types of uninformed search algorithms. In the next tutorial, we shall be discussing one by one in detail. So we have the breadth first search, uniform cost search, depth first search, depth limited search, iterative deepening search, and bidirectional search. Then another type of the search algorithms is the informed search or the heuristic search. Now, unlike the uninformed search strategies, this type of search strategy contains some additional information about the states beyond the problem definition. So this one uses problem-specific knowledge to find more efficient solutions. So it has additional information for each state, and therefore it will find a more or an optimal solution. So this search maintains some sort of internal states via heuristic functions. So these heuristic functions are the ones that will provide a hint to the agent. As the agent is searching using these algorithms, it will look for the best path for whichever state it's in. So that's why this informed search strategy is also called a heuristic search. Now there are basically two that types under the heuristic searches that we shall look at. We have what we call the best first search or the greedy search, and then we have the this star search, but this is read as a asterisk search. Friends, for today we are gonna stop from there. I thank you for being good listeners, good learners, good students. Don't forget to subscribe to my channel, and don't forget to call upon your friends to also come and join and subscribe. God bless you.